Aloha class, Polars intro part 2. Long story short, I just made a 28-minute video and my microphone was on mute. All right, so here we go. Got to do it all over again. So sorry if I'm not as enthused. Homie should have hooked me up. All right, here we go. Let's still roll. All right, last class. Example 2, right? Those were all circles. If it was cosine, symmetric about the x-axis. If it was sine, symmetric about the y-axis, right? These dudes were cardioids if the constant and the coefficient were the same. They were limitations, right? If the constant was smaller than the coefficient. And it was a dimpled cardioid or dimpled limation if the constant was bigger, right? But those are all examples of polar curves. All right, now what happens? What? That looks crazy. Now, example 4 and 5, you generally wouldn't have to graph by hand. So what we're going to do is we're going to kind of do these exploratory, okay? And believe it or not, these are roses, and roses have petals. How many petals could they have? But that, believe it or not, the number that's in front, which we'll call our coefficient, and the number with the angle are going to dictate how long your petal is and how many petals you have in your rose. All right, so let's all get out our calculadoras. Okay, so booyah, booyah, booyah. Come on, hopefully it will work. If not, I'll freak out if I've got to do this thing a third time. All right, but we're all going to go to mode. Okay, and we're all just going to explore. I got my little problems right here. You guys, I would suggest to graph it and take some notes and write down the important things we talk about in regards to these graphs. Go ahead and go to mode. Go down here to function and make sure you are in polar mode, okay? Now, if you notice, we're doing a lot of trigs, so we should already be in radian mode, so we'll check both of those right now, and then we'll go back to y equals. Now, let's go ahead and graph this first one, which would be 3 cosine of 3 theta. And let's see what happens, okay? And we're going to go ahead and hit zoom 6, okay, which gives us our standard viewing window. Okay, so there we go. We have a rose. Believe it or not, that 3 on the outside is the length of the rose, of the petals. So if you notice, the length of my petal is actually 3 units long. And then the 3 next to the angle actually stands for the amount of petals you have. Just like before, whether we were dealing with circles, cardioids, or limaçons, since it's cosine, it's symmetric about the x-axis. Okay, now let's go ahead and go to window. Something interesting about these particular roses, that if I go from 0 to pi, and it's important to check this, not 0 to e, what the what? 0 to pi. If you look, it looks like the same exact graph, and it is. And what that tells me, and it did trace this for us, and remember, we can go back here to window. I'm going to slow it down a little bit, 0.05. And the entire rose gets drawn from 0 to pi. And all that meant, because this was the same graph as we did earlier when it was 0 to 2 pi, it just traces itself. So it's important to note for this particular rose, it gets drawn from 0 to pi. It's important to note for this particular rose that the petal length is 3. It's very important for this particular rose that there's 3 petals. Why? Because there's a 3 up there, and then obviously it's symmetric about the x-axis. All right, here we go. Let's go ahead and go to y equals. What's next? What if I put a 2 out in front? Length of 2, right? What happens if I put a 5 right there? What do you think, class? Would there be 5 petals? And booyah, it is. Maybe that's pretty. Maybe bring that home to the wife tonight, right? Right? And so if you know, it's still symmetric about the x-axis. 5 petals. Why? Because 5 is next to that theta. How long are they? They are 2 units in length each. All right, y equals. Let's try the last one. Length of 4, right? And 7 petals for sure. Oh, that's pretty cool. They're longer. They're 5 units in length. That is even getting prettier. Maybe I could get like put all of these guys and give her all of these roses. All right, here we go. Let's go ahead and look at different. Now, how do you think the cosines and the sines would be different? All right, so let's go start. The first one was a 3. My bad. A 3. Let's go sine of 3 theta. Okay, so hopefully you're like, that 3 is probably a length of 3. That 3 next to the theta is probably 3 petals, and you're right. The only difference is it's sine, and what does sine tell us with the cardioids, limaçons, and circles? The signs were always symmetric about the y-axis. Will this one be? I bet you it will. Sweet, sweet. And the other important thing is this still, if I look at my window, is being drawn from 0 to pi. Okay, so it gets retraced from pi to 2 pi. Okay, very interesting to look at those. Now, if I were you, go ahead and put those other ones in there. But if you notice, right, the second example, 2 sine of 5, you'll have 5 petals. There'll be lengths of 2. It will still be symmetric about the y-axis, okay? But let's go ahead and look at my notes again, and let's pull this up a little bit. If you notice, there's something similar with example 4. And what is similar with this? 3 theta, 5 theta, 7 theta, 3, 5, and 7. Oh my gosh, they are all odd. But then if I look at example 5, they look like the same exact problem, but 2, 4, 6, 2, 4, they're all even next to the theta. Will that change what's going on? I want you to hurry up and take a guess and tell homie what you think. All right, let's go ahead. Don't you dare graph this. Don't be a cheater. Let's go with a, what do we have out here? We have a 3 out here, and we have a cosine, and we're going to go 2. What do you think the 3 does? Tell homie. What do you think the 2 does? Tell homie. Do you think it's going to be symmetric about the x or the y? Tell homie. All right, let's see if you're right. 3, that is the length of each one of those petals. Good job. 2, you probably said 2 petals. No. Believe it or not, when it's even, we're going to double that bad boy. So there's going to be 4 petals, okay? And then is it going to be symmetric about the x-axis? You bet, because it's a cosine. All right, here we go. Graph. What the heck happened there? That does not look like 4 petals. Do you know why? Oh, maybe it doesn't get the complete graph from 0 to pi. So let's change this from 0 to 2 pi and let's see what happens. Okay. 1, 2, 3, 4. There you go. It worked out, huh? Pretty interesting, but believe it or not, it doubles. So I don't know about you, but I want to look at this last dude right here. It says 6 theta. 6 theta, what the heck? That means there would be 12 petals. There's no way that could be possible. Oh, snap. Oh, I'm bringing that one home to the wife, right? That is parite, right? That's a beautiful one right there. Now, here we go. Let's go ahead and just finish what some of these looks like. I'm going to do the middle one here in 2 sine of 4 theta. I want you to give me some guesses right now. Tell Holmes if you want. How long are these petals? Dos. Oh, homie says, no way there's 4 petals. Remember, we double it when it's even, so there's going to be 8 petals. And then Holmes just told me, it's going to be symmetric about the y-axis, and it's going to be drawn from 0 to 2 pi. Why? Because it's even again out there. So boom ya. There we go. That's pretty. That's a little one. I'm going to bring the wife home that larger one that we saw, right? Right? Women like those big diamonds and those big roses. So, okay. Let's go ahead and write some conclusions here. All right, class? What do you notice about these graphs? And there's some very important things I want you to pay attention to. So here we go. First off, these are written as R equals, A cosine of B theta. And we have R equals A sine of B theta. The one thing I want you to note very quickly is if it's cosine, it's symmetric about the x-axis. Write that in your notes. And if it's sine, it's symmetric about the y-axis, okay? And then I want you to write these very important things here. If B is odd, right? That was the main difference because whatever A is, right, class? That was the length of the petals. You have B petals, okay? And it gets traced from 0 to pi. Okay, it's important to know. You're going to see why when we find the area of these petals. Really? We can find the area of those petals? That's when we put AB and BC together, ABC. Okay, if B is even, right, hopefully you can finish the rest of these notes, right, if B is even, because I'm going to have to, with my fancy pen, right, if B is even, how many petals do I have, class? Let's say 2B, right, we double it, so that'd be 2B. And when is it traced? It is traced from 0 to, say it, class, to pi, okay? Now, moving on, what we're going to look at is things that, we're hoping we start doing in some of our honors pre-calculus classes. We're going to look at what we call polar We're going to look polar to rectangular. So we need a relationship between our rectangular, which is x and y, and our polar, which is r and theta. Okay, and then we also want to go from rectangular to polar. Once again, I need a relationship between r, my x's and y's, and my theta and my x's and my y's. Okay, and so what we're going to do is we're going to look at these problems here. And they're all problems that could come up on the AP, kind of, sort of, a little bit, but kind of a backbone or a basis we should have had when we came into AP Calculus. Okay, so let's go ahead and start this first one. We have a little bit of a conversion, and they're asking me to convert from polar into rectangular. Okay, so there's polar, and I want to convert that into rectangular. Well, rectangular would be x comma y. Well, guess what? My x, if I want to relate that to polars, is just r cosine of theta. And my y is r sine of theta. Well, guess what? For this particular problem, I could convert that. My r is 2, and my theta is 5 pi over 6. My r is 2, and my theta is 5 pi over 6. Well, if you haven't noticed, you better be good at that unit circle, right? So if I convert this, it's going to be 2 times negative radical 3 over 2, which ends up being negative radical 3. That is sine 5 pi over 6 is 1/2, which would be 1. And you know what's very interesting? However you want to graph this, whether it be polar or whether it be in rectangular, I want to have a line. I get a point, boom, boom. I get a point. And the point would be about right there, whether you're on polar or rectangular, thus the conversion. Okay? All right, here we go. Well, now what if they ask us to go the other route and they give us something in terms of x and y, which would be rectangular, and they ask me to get into the polar? Well, we use these guys then. Okay, and I'm going to go ahead and I'm going to find my r, because at the end of the day, to convert that, I need it in terms of r comma theta, right? So my r is equal to the square root of x squared plus y squared, which would be 3 radical 2. Okay. But now I got to find theta, and the only thing that has a theta in it is that. So if I have to find theta, I'm going to use my y. And that's the reason why we use tangent, right, class? Because we have the y and the x. If not sines and cosines, I could use, but I would have to find r first, which I did do, so it would be plausible. But this here makes it a little bit easier. You get a negative 3 over 3, which would be negative 1, which where is cosine negative 1? It's in the second quadrant with a 45-degree reference angle, and in the fourth quadrant with a 45-degree reference angle. Now this one, though, we got to be careful. This here helps me to know what quadrant that's in, right, class? And that's in quadrant chi, right? Ichi ni san, okay? So believe it or not, it's not going to be that one for this particular problem. It has to be the one in the fourth quadrant. So it's 3 radical 2 comma 7 pi over 4. Okay, let's keep on rolling here. All right, here we go. Now, I'm not going to have my formulas up there, so make sure you're remembering. I'm going to remember. Got to be a little bit quieter. I got a resource over there, and they make fun of me. Can you believe they make fun of me? All right, here we go. Our next one, y equals, well, okay. That's in terms of rectangular, so I need a polar equation. Well, y is r sine of theta, right? And x is r cosine of theta plus 1. Okay, now, to get it into a polar equation, what I need to do is get r by itself. Well, to get r by itself, I'm just going to subtract that cosine over here. Okay, everything else has to come with it. Equals 1. I'm going to divide. I'm going to skip 2 steps, kind of 2 birds with 1 stone. And then I'm going to factor out that r, and then I'm going to divide, right? And there we go. I've got r by itself, and I have r in terms of theta, which would be a polar equation. Okay? All right, next up. Y equals 4. Well, once again, y is just this. Okay, and I'm really done, but I want to make it look fancy, so I'll get r by itself. I'm going to make it look super duper duper fancy and turn that guy into a cosecant, right? Not bad, not bad. Next one involves a little bit more. Let's see who is able to have that light bulb go out when we need it to. Go out, go on. Okay, r, x. That's my cosine, right? Y, that's my sine, okay, equals 16. Okay, let's go ahead and simplify a little bit, and I get this little fancy guy, okay? Right, and then hopefully you notice something there. I got a little sine squared plus cosine squared, and it works out beautifully when I actually factor out that r squared. And I remember, oh, that's the Pythagorean hopefully identity we all remember that bad boy right there is just Ichi. So I get r squared equals 16, which is r equals plus or minus 4. And you know what? You guys all saw that, and I know you knew that was a origin, a center that's at 0, 0, which I shouldn't really make a point there, and a radius of 4. And what is that? In polars, that just means go out 4 over and over and over again, whether it be positive or negative. We get the same thing. Well, we better get the same thing because they're equivalent. One in rectangular, one in polar. Now, why do we have polar? So we can get those sweet roses. Right? You can't do that in rectangular. There's no way, Jose. So to do the more elaborate stuff, that's exactly why we bring up polars in calculus. Enables us to do it, which if you ask me is super duper cool. Okay. All right, now we got polar equations, and I want to turn them into rectangular equations. Okay, so that means I'm just going to turn that r into x squared plus y squared. All right, now what the heck do I do here? Well, I can turn that cosine kind of into x's because it's x over r. Okay, now remember, this is really just the square root of x squared plus y squared. So when I multiply that on both sides, right, multiply it on both sides, I get the square root of x squared plus y squared times itself, which just gives me that, and I get that. And then you could easily solve that guy for y, right? I'm not going to take the time to do it, but if we wanted y in terms of x, it's kind of like how we want r in times of theta. You could go ahead and finish that bad boy, okay? This one here, a little bit different. I kind of can't go anywhere, but I want y's and x's in it. So if I want y's and x's in it, why do I want y's and x's in it? Because I'm going from polar to rectangular, right? Okay, so if I want y's and x's, and maybe one thing I could do here is let's take the tangent of both sides. If I do it to one side, I can do it to the other side, and I can turn this into y's and x's, right? It was up there, right? Up there in your notes, or maybe on the other page by now. But I get y over x, and then we all know that guy's in the second quadrant. It's a reference angle of 45 degrees, which would be a ratio of 1, but second quadrant, so -1, and then you get that. All right, and guess what? Let's graph this in polar. If I graph that in polar, that's that, right, class? And the negatives go that way. Oh, snap, that is exactly that line. Sweet. All right, what could I do for this last one? We would kind of get y equals. Now, the only way I could do cosecant, well, I got to turn it into y's and x's, but I can't. Sine is y over r, so cosecant is r over y. Now what I could do is I could maybe multiply that y on both sides, maybe factor out, right? Subtract it over, factor out. I get r equals 0, r equals 1. And believe it or not, that's it. Okay? You could have, some people would say, well, you could have just divided by an r and got y equals 1. But remember, it's never ever good to really divide a variable by a variable because you're eliminating some possible solutions. Okay? Now comes the fun part. B-O-T-C. Let me see it. B-O-T-C. Whew. Not bad. Could be the new fad. Okay, somebody come up with that cool new dance, B-O-T-C. All right, B-O-T-C, right? Bring on the calculus. All right, here we go. Let's bring on that calculus, right? Let's get some calculus. We've actually done no calculus yet. Okay, and what is the calculus? It's just like parametrics, dy dx. Remember parametrics, dy over dt over dx over dt. Guess what? Polars, dy over d theta over dx over d theta, or memorize that crazy formula. Okay, I am not going to teach you to memorize a formula. In the past, I have some students that like memorizing it, most of my students do not like memorizing it. So how could you do this if you didn't memorize it and they asked me to find dy dx? How could I do that? Well, this is polars. It's got a theta in it. So that means I have to find dy d theta over dx d theta. Now the problem is I don't have a y equation and I don't have an x equation. Okay, so maybe I need to create a y and an x equation. Okay, let's see if I can create one. Well, y is equal to r sine theta, right? And I know that from that previous pages, right, class? And x is equal to r cosine of theta. Okay, sweet, sweet. All right, so there's my equations, and they give me r. They say r is this stuff. So let's go ahead and create my y for this particular polar curve. And my y for that particular polar curve would be r, and r is 2 plus 2 sine of theta times sine. Okay. And I could actually simplify that to be 2 sine of theta plus 2 sine squared of theta, right? Okay. And then my x would be r, that guy right there, 2 plus 2 sine of theta times cosine of theta, right? Times cosine of theta. And that is equal to 2 cosine of theta plus 2 sine theta cosine of theta, okay? And then to get this answer, all I need to do is derivative of dy d theta, derivative of dx d theta. Okay, so let's see if we can do that. All right. Derivative of y with respect to theta. So let's take the derivative of that bad boy right there. I'm going to do it in blue here, or maybe purple, so I don't lose anybody, okay? And the derivative of 2 sine of theta would be 2 cosine of theta, right, class? This guy would be a chain rule. I've got to drop that 2 and it becomes 4. Don't you dare touch the inside times the derivative of the inside, which would be cosine of theta. Okay, so that's done. So that wasn't bad, right? Or you can memorize that formula. And formulas are really tough to memorize. Okay, but you would get the same thing if you use that formula up there. Okay, now I got to do dx d theta. So the derivative of 2 cosine theta would be negative 2 sine of theta. Oh, snap, that's a product rule. Okay, so let's go ahead and do 2 sine theta times the derivative of cosine, which would be negative. Ooh, so I'm going to put a negative there. Sine theta, which that would be sine squared theta, right, class? Okay, and then I have plus the derivative of sine, 2 sine, which would be 2 cosine theta times cosine theta, right? Or cosine squared theta. And then what this problem asks me to do is to find the derivative dy dx when theta is equal to pi over 2. Pi over 2, sweet, right? Because sines and cosines, it's either zero or ichi, right? So let's go ahead and get this guy. Now dy dx, is that even possible with respect to theta? For sure it is, because my whole entire equation up here is in terms of thetas. Okay, so let's see, put a pi over 2 in there, and cosine of pi over 2 is 0. Okay, put a pi over 2 in there, and sine of pi over 2 is ichi. Okay, put a pi over 2 in there, and my cosine of pi over 2 is 0. Oh, snap, so I get a 0 in the numerator. Okay, now it doesn't mean it's a horizontal tangent because I could get 0 over 0. That would not be a horizontal tangent. That would not be a vertical tangent. That's no part of the graph. Okay, does not exist. All right, let's go ahead and find the, plug a pi over 2 in the bottom. Let's plug a pi over 2 in there. Pi over 2 in there gives me a ichi. Okay, let's plug a pi over 2 in there. It'd be minus, right? 2. Plug a pi over 2 in there. I get a ichi. And I get a ichi, right? I get another ichi. But if I plug a pi over 2 into those, I get zeta, zeta. And so if I get zeta, 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 I get a negative 4 on the bottom, which is equal to 0, which means there would be a horizontal tangent at pi over 2. Pretty cool. Oh, all right, we got just one more to go. Just one, I swear to goodness, if this mic is not on, it better be on. I can't check you guys when I'm doing it. That's why I'm going cray-cray. All right, and look, it doesn't even go up. Do you know why it doesn't go up? Because I'm at the end of the page. All right, so here we go. Let's roll. And I'm going to have you guys do some work right now, okay? But they're asking me for horizontal and vertical tangents. Okay, well, everybody in this class knows to find horizontal and vertical tangents, I have to find the derivative. Now, this is the derivative, this is the derivative, this is my slope, right? My slope equation, but this is polars. So in able to do this in polars, I have to find dy d theta and divide that by dx d theta. Now, this problem's asking me, though, for a horizontal tangent, and it's asking me for a vertical tangent. And we all know we had to find the slope for that, so good, I'm well on my way right here. But the horizontal tangent would be, believe it or not, simply whenever dy d theta would be 0, right? And the vertical tangent would be ever when dx d theta is equal to 0. Now, if you notice, there's that nice little reminder there. 0 over 0, though, would neither be horizontal nor vertical. So you have to make sure you pay attention to that. Okay? Now, you are going to hit pause. Okay? Because it just gets tedious work if I do it all over again. Okay? You need to see if you can get this answer correct right now. When you unpause, the answer is just going to be up there. Okay? So make sure you do it. And if you don't get that same answer as I do, come in tomorrow for help. All right, booyah class, here we go. I'm going to change my marker here a little bit. Hopefully you got that. If you did not get that, class, please come in for help, okay? Because now I'm going to switch it up, and I want to find my HT, okay, my horizontal tangent. Able to find my horizontal tangent, right? We're going to set the numerator equal to 0, and I'm going to fix something right now, okay? But if you look at that top, if I set that top equal to 0, there's a major problem. Cosine, sine squared, cosine squared. It's kind of going to get me nowhere, right? And able to do something here and set something equal to 0, I'm most likely going to have to factor. And I can't factor if it has cosines and sines in it. So hopefully you're like, ding, 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 ding. Let's use this very important Pythagorean identity, that sine squared plus cosine squared is equal to ichi. So that means sine squared of theta is equal to 1 minus cosine squared of theta, right, class? So I can just substitute. And why am I doing this? Well, if I get everything in terms of cosines, maybe I can factor this bad boy and actually find out when it's equal to 0 and find some critical points. Haha, I can't. All right, so let's go ahead and distribute here. If I distribute, I get 2 cosine of theta plus 2 minus 2 cosine squared theta minus 2 cosine squared theta equals 0. Okay, and let's organize this a little bit better. I have 4 negatives of that bad boy. I've got a positive 2 cosine theta plus 2 equals 0. Kind of looks factorable, but let's go ahead and make it even look more factorable, right? We never want our squared term to be negative. Okay, so I do this little bad boy, changes all of those signs. I do a little factor. Oh, did I do that? Oh, I forgot a 2 there, right? How come somebody didn't tell me that? Okay, 2 right there. I'm glad I caught it. Oh my gosh, now I'm forgetting S's and 2's and all that stuff. Okay, this would be plus 1. This guy would be cosine of theta minus 1 equals 0. Let's check, do a quick check. That checks out. Ooh, I'm running out of space here. So I get 2 cosine of theta plus 1 equals 0, which would mean cosine of theta equals negative 1/2. Okay, and then my other one would be cosine of theta minus 1 equals 0 or equals 1. Okay, so I'm running out of space. I'm sorry here, class. We're going to come up here, okay? So if cosine theta is equal to negative 1/2, what are my 2 answers? My 2 answers are, where do I got it here? Ooh, I got it over there. 2 pi over 3 and 4 pi over 3. Okay, 2 pi over 3 and 4 pi over 3. Now it says beware of 0 over 0 because what that means is if I plug a 2 pi over 3 into this guy, okay, or if I plug it into there, I'm going to get a 0. If I plug a 4 pi over 3 into that top part, I'm going to get a 0. Now if I got a 0 on the bottom too, that would not be a horizontal vertical tangent. So I'm going to just check it real quick. No and no. And the reason why I know it's not 0 over 0 is because I just got to plug it in there and I'm good to go. Okay, I'll get at least some type of an answer, okay? Or I guess they could cancel them out. So let me check. We're good to go, okay? And you should check those. Now, cosine theta is equal to 1. Now, when is cosine theta equal to 1? At 0 and at 2 pi. Well, are those guys going to both be okay? Let's go ahead and check it out. Well, I really just have to check the bottom, right? Let's go ahead and put a 0 in there. That'd be 0, 0 in there. I get 0 over 0. That means 0 over 0 is no good. That means 2 pi is no good because it's going to give me a 0 over 0. So that's the only correct answer there. And my pen ran out, and that's okay because you're going to do the rest on your own. Okay, what do I mean by do the rest on your own? You have to find the vertical tangents. How do I find the vertical tangents? You have to set that equal to 0. Now, if you set that equal to 0, I got my answers right here. You should get pi over 3, 5 pi over 3. You should get, what else do I got? What else do I got? 0 and pi. We already just found out that 0 does not work because you get 0 over 0. But those 3 do work. Aloha! The mic better have worked!